So how exactly do you build a high-level Java-style list interface inside a purely procedural, bare metal language like C? Honestly, it's a massive architectural challenge. C doesn't have classes, it absolutely does not natively support object-oriented inheritance, and memory management, well, that's entirely manual. But despite all that, developers consistently find these ingenious ways to force high-level paradigms into this really gritty, low-level environment.
Welcome to this explainer. Today, we're going to unpack exactly how one specific library, the electrostatic sandbox, brilliantly pulls this off. We're going to look directly at its source code, and as you'll see, it just seamlessly blends low-level memory control with some truly high-level architectural design.
Okay, let's dive right into this. Here's our roadmap for today. 1. Automata blueprint. 2. Designing the list ADT. 3. Solving cyclic dependencies. 4. Buffer mechanics, and finally, 5. Clock and memory complexity. Let's get to it. Now, before we look at the code itself, it's always great to kind of humanize the architecture. This code base was authored by developer Pavli Gurgis. And what makes this particular repository such a joy to study is that the author didn't just write the code, they actually left these incredibly detailed, almost documentary-style developer notes throughout the headers and source files. It's honestly like having the architect give you a personal tour of the building.
Section 1. Automata Theory Blueprint.
You know, you might expect a C data structure to just start slinging pointers around right out of the gate, but this one, it begins with a really strict philosophical foundation. Right at the top of the list.h file, the author grounds this procedural architecture in the scientific ontology of finite automata theory. So essentially, they're treating the C program as a state machine. The documentation explicitly states that they use constructor routines as the actual mechanism to change the direction of the deterministic automata in procedural programming. Pretty wild, right?
Moving on to Section 2, Designing the List ADT.
Let's see how this builds out from that theoretical blueprint straight down into the abstract data type, or ADT layer. The repository outlines a strict, hierarchical architectural pattern for its list ADT. Right at the top, you have the general list concept. But underneath that, it branches out into highly specific buffer implementations. So you have the contiguous buffer, the linked buffer, and the memory pool buffer. And it doesn't even stop there. The linked buffer breaks down even further into doubly linked, circular, and unrolled variations. It's basically a classic object-oriented inheritance tree, but mapped out entirely using pure C structs and headers.
Now, what's really fascinating here is how they actually achieve that true OOP interface feel. They use a struct called list_function table. And this table is just packed with C function pointers, things like add, insert, remove by index, and iterator. By binding these function pointers to a specific list instance when it's initialized, the C struct behaves almost exactly like a Java interface. You literally just call the function from the table, which completely abstracts away whether the underlying memory is contiguous or linked. It's a really brilliant workaround.
Up next, Section 3, Solving Cyclic Dependencies.
If you've spent any time writing in C, you absolutely know that as your project grows, headers just inevitably start including each other and boom, you're stuck in the dreaded circular dependency loop. Well, the electrostatic sandbox solves this so elegantly. The author created a dedicated utility file called types.h. This file contains dozens of incomplete type declarations, which is basically just telling the compiler, hey, a struct exists, without defining its actual contents yet. So, instead of the list headers and the utility headers constantly cross-referencing each other, they all just point to types.h. It acts as this master registry. The dev notes actually point out that this entirely bypasses the cyclic headers processing issues that usually pop up when libraries and utilities are forced to interact.
Section 4. Contiguous buffer mechanics. With the architecture safely organized, let's step directly into the engine room to look at the gritty reality of memory allocation inside the contiguous_buffer.c implementation. Whenever you add or insert an element, you run the risk that the buffer might run out of space, right? The codebase handles this with what it calls a stretching algorithm. First, it checks if your target index hits or exceeds the current buffer limit. If it does, it dynamically resizes. But, and check out step 2 here, it doesn't just multiply the size by 2 using standard math. No, it uses a bitwise left shift. It calculates the new limit as the index shifted left by 2 plus 1. This bitwise operation is incredibly fast at the CPU level. Finally, it just delegates the actual memory reallocation to a dynamic update function. Finally, Section 5, Clock and Memory Complexity.
I really want to focus on the fascinating inline performance analysis provided by the author here. It is so rare to see a developer do deep mathematical complexity breakdowns right there inside the C file. Look at this excerpt documenting a function called unsafe left shift items by 1, which they use during element removal. The dev notes break down the deterministic clock complexity. Because it's a linear shift of elements, the author notes that the clock complexity actually gets better when the removal index is near the end of the structure, simply because there are fewer elements to shift, and worse when it's near the 0 index. It just gives reading the code a real, behind-the-scenes mechanical feel.
And this brilliantly illustrates the strictness of their memory profiling. Right in that same comment block, the author breaks down the memory complexity. They note that the heap complexity decreases by a unit of 1 for the specific element removed. Because the array holds memory addresses, which of course are 8 bytes on a 64-bit system, the dev notes track this as a strict constant ratio. For every one element dropped, exactly 8 bytes of heap complexity are reduced.
So the absolutely crucial point here is how aggressively this library guards its memory bounds. Inside the contiguous _ buffer memory update function, the exact start address and end address of the buffer are constantly recalculated. The code explicitly mandates that this dynamic update must occur on every single write operation. Add an item, recalculate the partition bounds. Remove an item, recalculate the partition bounds. This strictness ensures that the theoretical automata state we talked about earlier always perfectly matches the physical memory state.
We really take high-level lists for granted in languages like Java or Python, don't we? But seeing the bitwise shifts, the interface function tables, and the relentless memory bounding in pure C reveals the incredible engineering keeping our software running under the hood. So I'll leave you with this to think about. Does your favorite everyday data structure strictly define and verify its low-level memory partition bounds on every single write operation? It's definitely something to consider next time you simply type .add. Thanks for joining me on this explainer, and keep exploring the code.